In the previous video, we looked at examples of how to find the general solution for antiderivatives. This video is all about particular solutions. So what's the difference between a particular solution and a general solution? Well, a general solution is an answer that has plus c in your answer. A particular solution is when you don't have the plus c in your answer. If you're given a point on f of x, which is called an initial condition, then you can use this to solve for the c and then find the particular solution. That just means that you're finding the exact value of what was an unknown constant. Let's look at an example of how to do this. Let's say if we have f prime of x is equal to 1 over x minus 4. And we're also given that f of 5 is equal to 3. That f of 5 equals 3, that is our initial condition. Before we can find the particular solution, we have to find the general solution. Let's try using the power rule for antiderivatives. I'm going to rewrite f prime of x as 1 times x minus 4 to the negative 1 power. Using the power rule for antiderivatives, we would have 1 divided by the original exponent of negative 1 plus 1 multiplied with your base, x minus 4, raised to the negative 1 plus 1. But wait a minute, there are some problems here. This would simplify to 1 divided by 0, which would be an undefined answer, and then the parentheses, x minus 4, would have a 0 exponent. That means we did something wrong. It's important to note that we cannot use the power rule for antiderivatives whenever the exponent is negative 1. If we do, we're going to end up with an undefined answer, which just isn't right. Instead, we have to realize that the antiderivative of a function like this is a log function. So then we need to use what we know about taking the derivative of a log function in order to find this other antiderivative. If we took the derivative of the natural log, we would take whatever is inside of the log, in this case x, and put it in the denominator. And then you would multiply this with the derivative of what's inside of the natural log. In this case, the derivative of x is just 1, so our final answer would be 1 divided by x. If we're working backwards and finding the antiderivative of 1 over x, that would get us back to the original ln of x. But remember to be careful here. When you take the antiderivative of 1 over x, you have to put in absolute value bars around that x. So let's get back to our original problem. F prime of x was 1 over x minus 4. Since we have 1 divided by a function of x, that tells us that we can use a natural log to find the antiderivative. Whatever's in the denominator of our derivative goes inside of the natural log. And since we're done with taking the antiderivative of that term, we can add a plus c at the end. This is the general solution. Next, let's apply the initial condition of f of 5 equals 3. Begin by just writing down your initial condition, f of 5 equals 3. And then we can set this equal to our general solution, which is the natural log of x minus 4 plus c. But instead of writing in an x, we're substituting that 5 in for the x. So that means we'd have the natural log of the absolute value of 5 minus 4 plus c. Now we have an equation whose only unknown is that value c. So let's solve for c. First, we can simplify the natural log. The absolute value of 5 minus 4 is just 1. The natural log of 1 is equal to 0. Therefore, c is equal to 3. Now we just need to substitute that value of 3 back into the c inside of our equation. F of x would then become the natural log of the absolute value of x minus 4 plus 3. And that is the particular solution to our problem. Let's try one more problem. F prime of x is equal to e raised to 5x. We have the initial condition that f of 1 is equal to e to the 5th power. Pause the video now and try this on your own. First, let's find the general solution. We haven't found an antiderivative of an exponential yet. Well, if f of x were to be equal to 5e to the 4x, to find the derivative, we would just copy and paste f of x. So we have 5e to the 4x, and then multiply that times the derivative of the exponent, which is 4. Since we're finding the antiderivative, instead of multiplying by the derivative of the exponent, we're going to divide by the derivative of the exponent. So here's what I mean. The original problem, f prime of x is equal to e raised to the 5x. Let's copy and paste that equation, e to the 5x. Since my exponent is more complicated than just an x, I have to take the derivative of the exponent. And when we're finding an antiderivative, we would divide our answer by the derivative of the exponent. And now that we've found the antiderivative of the e to the 5x term, we can add a plus c at the end. This is our general solution. Next, let's rewrite our initial condition. F of 1 is equal to e to the 5th power. And we can set this equal to the general solution of e to the 5x over 5 plus c. Instead of having an x inside of our general solution, we substitute in the 1 that's inside of the parentheses. So inside the exponent, we'd have 5 times 1. Now we have an equation that has only one unknown, c. That means that we can solve for c. In order to do this, we need to move this term over to the left side of the equal sign. That would give us e to the 5th power minus e to the 5th power divided by 5. This is equal to c. We can multiply that left term by 5 over 5 to find a common denominator. Then we can combine these two fractions. 5e to the 5th power over 5 minus e to the 5th power over 5 would be 4/5 e to the 5th power. This is what our c is. We can plug this back into the general solution. We can substitute this value into the c inside of the general solution. That would give us f of x is equal to 1/5 e to the 5x plus 4/5 e to the 5th. We first found the general solution for f of x. Then we use the initial condition to find specifically what c is equal to. After substituting that into the general solution, we then found the particular solution for f of x.